Hello everyone, thank you for coming. The subject of my presentation is cloud detection and classification algorithm for Himawari image measurements based on deep learning. My report will start from the following four sections. Firstly, let's introduce the research program. As we know, the cloud affects the short-range weather program and the climate change and atmospheric circulation by regulating the global radiation budget. Satellite observation provides an effective ways for monitoring the Earth's atmosphere system over the region and global scale in the high spectral temperature resolution. Cloud detection and classification is a representation for the retrieval of the cloud microphysics parameters and fields obtaining the surface radiation patches for the satellite-based multispectral observation. In the past, there are lots of cloud detection and classification algorithms proposed and implemented for the measurements from the various space optical series. Cloud mask algorithms are typical designed to use a series of tests of decision tree involve multi-threshold. Traditional cloud face detection algorithms are based on the reflection difference and blood temperature difference between two channels. Furthermore, more accurate detection of the multi-cloud is a more complicated issue. Multi-cloud detection is typically influenced from the disagreement between the relative SWR shortwave influence and TIR thermal influence cloud phase. Uh, in this study, deep learning-based algorithm is developed for the simulation cloud detection and cloud phase classification and multi-layer cloud detection from AHR measurements. The estimate of the data sets and the deep learning-based algorithm are shown in the section 2. In this section, first we based on the radial transfer model to grasp the feature of the different spectral channel and their potential importance. Therefore, before developing the algorithm, the spectral feature and different cloud conditions are simulated. The radial transfer simulation is by the radial transfer model named ERTM. The ERTM model includes the CKD method for the gas observation and parameterization for the cloud optical property, and the adding method for force stream for infrared radial transfer. It can simulate blood temperature observed by the AHR and clear and cloud atmosphere. The parameter law based on the combination of the observation radius and the clear scale radius is introduced in the formula, where this is means the observed temperature at the lambda channel, and the basis is means the simulation clear scale temperature for background atmosphere profile. The advantage of these parameters is that it can account for the clear radiance. Since it can eliminate the interference from the background atmosphere and surface condition. It is evidence that the reflection difference method can achieve some successful in the phase classification, but the scale of the reflection difference method is limited under the optical thin cloud condition, as the reflect difference is close for zero for either ice clouds or water clouds with a small optical difference of optical thickness. The brighter temperature difference method suffices for the simulation problem. However, the parameters law gives more comprehensive information on the classification of cloud face. This use of low subsystem improves the discrimination of the optically thin clouds, which is significantly superior to the RD and BDR method. The sensitivity study reveals that the account for the simulated clear scale radius can eliminate the interference from atmosphere background signal, and the subsystem improves the detection and the discrimination for the optical thin cloud. Therefore, DNN models are designed for the simulation, the cloud detection, and cloud cloud face classification, and multi-layer cloud detection for the multi-factor observed radius and simulated clear scale radius. The measurements for the space-borne active uh, sensor, such as CPR and Calypso, are frequently used as the benchmark to assess the cloud and aerosol retrieval products. Taking advantage of the LiDAR and radar CPR measurements, cloud product suppliers are more completely cloud vertical structure and more reliable cloud face uh, de- determination for each cloud layer. Therefore, the CPR Calypso measurements cloud product from the 2016 are used as a reference label for the train datasets. The HR observation and the meteorological fields data are collected as with the measurements cloud products and the quality control. ERTM radial transfer model is used to simulate the cloud radius from the atmospheric profile, surface condition, and the viewing angle. The 2D model are estimated for all scale and day-only application, respective. The all-day model uses the observed radius and class gradients from the 8T-IR channel as a predictor. When the daytime model uses both TIR and 6 VNIR channels radius as a predictor. More model evaluation with independent dates and official models AHR channel are presentation in the section 3. For the independent evaluations, data sets from 2016 is used to validate the estimated DNA model. The results show that the inclusion clear scale radius from DNA model is conducive to improve the cloud detection and classification, and also indicated by the sensitivity study. The overall evolution of all scale and daytime DNA model reach about 81% and 84% respective. Several evaluation metrics are used to assess the performance of the DNA model for cloud detection and classification. Two evaluative cloud masks each sample are classified as clear and cloudy events, uh, respective. Then the probability of detection (POD) and the phase alarmation (FAR) for the clear and cloud are defined as the list form. When this TCLA and TCLD are the number of the IQ clear and cloud pixel respective which are correctly identified by the DNN models, while FCL and FCLD are the numbers of the clear and cloudy pixels that are first identified the DNN models. PDO, also called recorrelation, reaches its best value as 1 and its worst value as 0, while FAI is supposed to be a low value close to 0. Besides, two evaluation metrics are also introduced. They indicate the overperformance of the DNA model in cloud detection and shows a high detection level as it approaches 1. The evaluation matrix of the cloud mask shows two DNA models achieve successful performance when HR value is higher than the 0.95 and KSS values about 0.88 overland over the all day and DNA model outperforms the Modis and AHR cloud mask, which have relative low HR and KSS values. Over the water surface, the DNA model and the Modis product work fairly well and perform better than the AHR model. For multi-layer cloud detection, the results show that the DNA model and the two products show that under sync cloud condition, uh, the property of the multi-layer cloud detection reach 61 percentage for the DNA model and 68% for the day model, which is obviously better than the Modis and AHR product results. For thin clouds, the DNA model performs slightly better during the less misclassification of the multi-layer clouds and mixed phase clouds. So the core rate of the multi-cloud reaches 63 percentage and 75 percentage for DNRD model and daytime model respectively, while the Moody's products classify the most thin clouds as the single layer cloud. To better evaluate multi-layer cloud detection, this figure shows that the property of the DNA models and two official products correctly identify a multi-layer cloud, varying with the separation distance between the base of the up ice cloud and the top of the low water clouds as shown in the figure. The property of the multi-layer cloud detection by the Moody's product increasing with the upper layer COT, but shows little dependence on the separate distance. However, the multi-layer cloud detection results from the AHR product weakly depends on both the upper layer COT and separate distance. In Figure C and Figure D, two models show the similar characteristics that the property of the multi-layer cloud detection shows that little depends on the upper layer COT when this separate distance is larger than 4 kilometers. Multi-layer cloud could be detected by DNA models with stable results. For single cloud face discrimination, the POD values of two models are um, higher than 0.898 with the FAR values and less than 0.02 for both water cloud and ice cloud. The evaluation matches of two DNA models for face direction is slightly higher than this Modis and AHR product, and improvements are more notable over the land than over the water surface. Furthermore, the difficulty of the cloud phase direction is composed by the mixed phase function identified since water and ice clouds could both easily confuse with the fixed phase cloud. Single layer mixed phase clouds identified two models are also investigated shows that the DNA model can identify the mixed phase clouds correctly with the HRS above the 86% and 93% over the land and water surface respectively. The DNN model are applied to this case over the eastern region of tropical Indian Ocean. Figure A shows a natural cloud image of AHR channels. Along the obliquity, there are two types of cloud. High-level clouds over the Caspian Sea west of Sumatra and Java, and west area of the low-level structure of the west coast of Australia. The high clouds advantage over the wide region of the low structural cumulus as is shown in the figure. Figure B, uh, figure F shows the results of the from DNN model and two official products with the measured cloud products along the orbit. The vertical profile of cloud thermodynamic physics from the CPR CIOP along the orbit shows in the figure G. As is in this figure, DN model has the better capability in detection the optically thin series. However, the modest and AHR product omitted this thin series. Besides, in the supple dotted box, multi-layer cloud detection by the DN model is more consistent with the CPR Calypso than two official products. Mixed phase clouds also shows in the case of the region are detected by the CPR Calliope measures. The DN model correctly identifies these mixed phase clouds, which, however, is identifies the multi-layer clouds by the models and AHR products. Finally, let's briefly my report. A deep learning method based on cloud detection and classification algorithm for the AHR measurements from the Himawari 8 has developed. It ensures that DNA models outperform the official models and AHR products in cloud detection and face discrimination, and the enhanced is more significant over the land, over the water surface. DNA models have superior capability in detection the optical thin clouds. Circulars DNA model also shows the effective mixed phase cloud identify. Multi-layer cloud detected by the DNA model is more consistent with the CPR Calliope and the two official products. Okay, thank you.